Okay, so in this video, we're going to do the two samples t-test for paired samples. So when you think about two sample t-tests and you have paired samples, then we have the same group, but we have before and we have after. So if it's in the pharmaceutical industry, then we have before, then we have some kind of a drug intervention, and then we have after. If it's in marketing industry, then we have before revenue or conversion rate, and then we have some intervention, maybe some new app is released or some new discount is offered, and then we have after, comparing revenue before and after. Okay, so revenue or conversion, like somebody visits a website and do they buy something or do they get a membership? And so we're testing before and after. This is like in A/B testing, you might have this scenario. Okay, so the concept is very simple. We have the same group before and after. We take a random sample and we want to come up with a set called the difference. And we're going to use that difference and do a t-test on that. So we're going to do a one sample test for paired samples. Okay, so let's take a look at this example. It says a car manufacturer wants to determine if a new fuel additive will increase gas mileage. Okay, so we want to know if we put in this new fuel additive, will there be an increase in the gas mileage? Okay, so a random sample of 10 cars, so we've got a small sample, is selected, and their gas mileage is measured both before and after. So we've got before and after. And from these two sets of data, before and after, we get this set D called the difference. So in order to get this 10 here, we would take the after minus before for each level. So this might have been like 30 minus 20. This might have been whatever, 24 minus 12, and go on like this. Okay, so that's where this D set of numbers D comes from. This is the difference in the set. This is the difference in the gas mileage before and after using the fuel additive. And we want to know if there's a significant difference at the 5% level. Okay, so the 5% level is pretty much standard across industries, and in some cases you might change that, but usually that's it. So in order to do the t-test on this set of differences, we need to find the mean and we need to find the standard deviation, which I've already done that. So let's go over here and check it out. All right. So we've got our mean value, we've got our standard deviation. And then also let's remind ourselves that the alpha level is at 0.05. And then here we've got that our population mean. So our null hypothesis is that our population mean of the differences is 0. So let me just explain a little bit more about what that means. It means that if we look at our mean from before, well, okay, so let me explain like this. So what do we want to test? We want to test to see if our mean for after is greater than our mean from before. And if it's not, if there's no difference between them, then if we were to subtract them, we would get 0, right? So that's where we get this idea here, that the mean of the differences, the true population mean of the differences is 0, meaning that the fuel additive didn't increase the gas mileage and it didn't decrease the gas mileage. It did nothing, right? Okay, so our alternative hypothesis is that this is true, which would mean that if this were true, so if this is false, then we get this situation here. Well, not entirely. So I guess here we're assuming that there's no way it could possibly reduce the gas mileage. It could either be 0 or it could be positive. Okay, so that's just a subtlety though. So let me go here though. If this is true, so if this is true, then that means that if I subtract them, then I'm going to get a positive number, right? Which is how we have this as our alternative hypothesis. Okay, so hopefully that's clear. So then what it means is that we have a one-tailed test. Okay, and so when I look at let me get rid of all this stuff. when I didn't get rid of that. When I look at my PDF, so what I'm going to be testing is we're going to be going from positive infinity. Wait a minute, that doesn't make sense. Oh yeah, yeah, it doesn't make sense. So I'm going to be going from my t-score to positive infinity because I'm doing. I want to know if there's an increase, and it's going to be one test. Okay, so basically, it's going to be looking like this, and over here is going to be. I'm going to be testing for some t-value over here. Basically, if my p-value is past some point over here, then we're going to get less than 5%. So we're going to less than 5%. So of the area, then that's going to be rejecting the null hypothesis. Okay, so then let's see, what do we need to do? We need to calculate the degrees of freedom. In this case, the degrees of freedom, because it's like a one sample now, since we've taken the difference, is going to be n minus 1, which is going to be 10 minus 1, which is 9. And then we need to calculate our t-score. Now, in this case, our t-score is a little bit different because of the fact that we're looking at the mean value of the differences being equal to 0. Okay, so then what we're going to do here is say our t-score is the mean of the differences minus 0. Okay, because that's our hypothesis about the mean of the population of differences, is that it is 0. Okay, so typically would do like x bar minus the mean. In this case, we're making the hypothesis that the mean is 0. So that's where we're going to get this calculation. And then we're going to get our standard deviation divided by the square root of n, as usual. And so here we'll get 11.4 minus 0. Divide that by 1.32 divided by the square root of 10. And when you do that calculation, you're going to get 16.47. Okay, so here's our t value. So what I want to do, I want to integrate from 16.47 to infinity. And this is the first method, okay, p-value method. And I want to see what is my p-value. If my p-value, p is less than alpha, then reject h naught. And if p is not less than alpha, so I guess I could say, well, it just looks like an infinity symbol. So p is not less than alpha, meaning this, then we fail to reject. We do not accept anything, we just fail to reject. Okay. So what does it mean? But okay, so it sounds like we're being tricky, saying something slick, but now it just means that we're taking into account the probability of a type 1 error. So if we fail to reject the null hypothesis, we don't accept the alternative hypothesis, but we can say that the evidence supports the alternative hypothesis, like 95% probability. Okay, so then let's go to Wolfram, and we will set up this integral. And actually, I just realized I'm not really sure what p-value I'm going to get. Hey, what happened? Oh, no. No. What happened? Okay, there we go. Somehow I like broke it or something. Okay, so I guess I got to leave it like this. So I've got my integral in here, and I just need to go in here, and everywhere there's a v, I'm going to put in my degrees of freedom. Now, like really, in real life, you're never going to do it this way. I'm only doing this just for demonstration purposes. And in fact, don't forget, I have more videos coming soon after I finish all this stuff, where I'm going to show you everything, how to do this in Python. How to, let's say you've got a data set with columns and different levels of categorical variables where you want to test them. using t-distribution. That's the ultimate goal of this whole thing. Okay, now this should be correct. Let me just check it. All right, here we go. And we get, definitely, this is below 0.05, 10 to the -8. So if you don't know what that means, it means that there's going to be 7 zeros in front of this 2. Okay, so definitely the p-value is less than alpha, which means that we would reject the null hypothesis, which means that the evidence supports the alternative hypothesis that the additive had a positive effect on the gas mileage. So in fact, we call this the lift, if you like. Okay, so we could say that at the 5% significance level, the evidence supports that there's an increase in the gas mileage by using the fuel additive. All right, so then let's see. Now, the next thing we're going to do is look at the critical T method. So to do that, we're just going to use our T table. So what do we need to use our T table? Well, we have to know, do we have what kind of a test do we have? In this case, we have a 1-tel test. And it's right tel because we're interested in the increase. And we have alpha of 0.05. And what else do we need? We need alpha. Oh, we need degrees of freedom. Yeah. So our degrees of freedom is 9. So let's go take a look at our T table. And get bigger. Oops, wrong button. All right, so I'm looking over here at my T table. And you should be 2 now. All right, so here we go. So let's go find degrees of freedom is 9 here. And remember this T table that I'm using, it's from the University of Utah. And it gives us the upper tel. So we're looking above the T value. So here we get 9 is our degrees of freedom, and here's our alpha level, 0.05. So just going down to here, and we get 1.833. So certainly our T, so let me go write this over here. Certainly our T value is huge compared to this one, right? So T equals 1.833. That's our T star. And our T value is like 16 something. Right. So by this method as well, we can see that we would have to reject the null hypothesis. So let me take a look at the graph then. Now, again, we're doing a 1-tel test, but my graph has both tells. That's fine. So here it is. So here you can see our T distribution for degrees of freedom equal to 9. You can see it's like a lot skinnier than the ones we've been seeing. Here is our T critical 1.833 here. We're not really worried about this, but the function I wrote to create these graphs always graphs both of them. So, so that's why that's there. But we're not really worried about this end because we're only worried about if it's greater than. And then here's the T-score way over here that we got 16.47. So it's well away from our fail to reject region, which is here. Here's our fail to reject region. And anything that's in here or over here is in our reject region. And you might say, well, how's it possible? Because look how far away it is. Well, actually, you've got to remember that these PDFs are, they have infinite volume, is it? I'm not sure. Anyways, we're going from negative infinity to infinity, right? But it just so happens that the area under it is 1. So you could continue, you could have T-scores all the way up to whatever, and the area would only always be 1. But anyways, this thing's definitely in the reject region, well into the reject region, which means we reject the null hypothesis. And so then what I would say, if I had to write a report to my stakeholders or to my team or whoever, I would say something like this. Let's see. Let's say based on, well, let me say it like this. The fuel additive increases the gas mileage. Now we didn't get into like how much it's increasing, right? We did get into it, it's increasing. Increases the gas mileage of the vehicles. And then we would say something like increases the gas mileage of the vehicles. 95% probability. Okay, but maybe you might not want to include that last statement. So again, when you're talking to stakeholders, unless they ask you, or unless you're familiar with them and they are interested in knowing these kinds of mathematical details, you're better off leaving that out because it's something else you'll have to explain. And if you do, maybe you do. If you don't do a good job of explaining it, then maybe your whole recommendation or analysis is tanked because they don't know that 95% probability is the best you're going to get, really. I mean, you could do better if you change the alpha level, right? But or just that when you're speaking in a business situation, people don't want to know or care to know the mathematical subtleties. So the fuel additive increases the gas mileage of the vehicles. Yes. Okay, so, and then maybe you want to say something more like based on, so that's much better, isn't it? Based on our analysis, and then maybe let's add this in here. Statistical analysis, the fuel additive increases the gas mileage of the vehicles. Right, okay, so that would be it. And then you probably would want to include some information, if we can, about like how much, like what's the margin there that we're talking about. And so that's it for this one. And then our next example, let's see, what is our next example? So then, oops, I should probably get rid of this, right? Hold on, let me see if I can erase this. Okay. So in our next example, let's see, I'm probably going to skip that. Our next example, and then I think it's our last example. I'm going to show you how to do a t-test when we're testing for a proportion. So this is different than what we've been doing, because so far we've been looking at continuous variables and looking at continuous, looking at things like means, statistics that are associated with continuous variables. But when we're looking at proportions, we're looking at categorical variables, and we're looking at frequencies, and so we're testing proportions of populations. And so it's slightly, it's not much different, but you have to keep in mind that when you're dealing with proportions, a proportion is normally, so the underlying distribution for proportion, like if you're not using a t-test, it's a binomial distribution that can follow a normal distribution. So there's something in that, which I'm not sure if I said that right, but it's a little different. And so we'll go over that. And then after that example, we're going to jump into Python implementation. And they'll have one more video on implementation in R, and then the series will be complete. Except for there may be some bonus materials where I demonstrate how we use the t-distribution in linear regression models when we're selecting parameters for the linear regression model. And also one other thing that I forgot. So it's in the previous video. So that's going to be it for today. Thanks for watching. I hope this helps. If you have a comment or suggestion, or if you notice an error, or if I misunderstood a concept, please tell me. All right. Thanks.